My name is Mark McClain. I am a senior principal architect at Yahoo, and also currently am a member of the OpenStack Technical Committee. Previously, I served as the program technical lead for Neutron during the Havana and Icehouse cycles. So what I want to do is touch a little bit on, Asaf covered a good chunk of Neutron earlier, and so I wanted to touch on a few more parts of it. One of the motivations that we missed earlier is why did we create Neutron originally? Is we wanted to provide a way to access new technology within OpenStack. We also want to provide tenant isolation, enable deployers to develop rich topology, so multi-tier network architecture, as well as provide support for advanced services, including load balancing, VPN, firewall. Just a couple of basics if you're not very familiar with either OpenStack or networking. The first thing is when we take a look at the OpenStack in general across from the compute API, the network API, and the storage API, one of the things is that those APIs are generic facades into the underlying technologies, whether it be KVM in the case of hypervisor for networking, the ML2 plugin, or in storage API, Ceph. A couple other abstractions we see that you'll see frequently when we have network discussions is when we talk about virtual server instances, that's the orange boxes up at the top. The black boxes right below it are VIFs. Think about them as network cards. And those are typically managed by Nova. And then in the separation of powers, we have Neutron, which does virtual ports. It's equivalent to a switch on a port on a switch. The L2 network, which is a shared broadcast domain, and then the virtual subnet, which is the address range, typically an IP for IPv4, IPv6. So for our architecture, when we designed Neutron, some of our design goals were ensuring that we had a unified API, regardless of the underlying technology. Again, that goes kind of to match earlier with what I said with how the compute API and the storage APIs are constructed. We wanted to have a small core so that it makes it real easy to implement, to build an implementation. We also wanted something that was very pluggable and had an open architecture. One of the reasons for that is we wanted to provide multiple vendor support. So as you see these logos dropping in, you'll see we have 19 different plugins available in Neutron. So it gives deployers lots of choices. You can either make your decision based on existing equipment you have in your data center, or if you're purchasing new equipment, you have lots of choice in terms of vendor selection. We also wanted to make something that was very extensible. Mainly because if we want to enable new technologies, it does take some time to standardize on what the technologies look like. We also wanted to provide an opportunity for the vendors to differentiate themselves. Extensions is one of those mechanisms where a vendor can expose new features that are unique to their offering. It wouldn't be an OpenStack presentation if I didn't show this diagram. I think it's also required. And what I want to do is focus a little bit on the right-hand side, which is the Neutron Server part. Typically in a basic deployment, Soft covered this earlier, so I'll fast forward through a few bits. But we have the Neutron Server. It's backed by a database. We have a message queue, which then relays messages to multiple agents. In a typical deployment, you'll see an L2 agent, a DHCP agent, an L3 agent, an advanced services agent. And if you notice, you'll have multiple copies of these pop up, because in real deployment, you'll have multiple L2 agents. The reason we use a message queue is that way the agents and the server do not have to directly address the other. So if we dive in a little bit more into the Neutron Server, the Neutron Server is really built up of three parts. You have the REST API service, the RPC service, and the plugin service. And taking a look at the REST API service, it's a HTTP Python WSGI application, typically runs on 9696. And what it's going to do is it's going to expose our logical resources. So earlier when I talked about one of the original goals of Neutron was to have a small core. The resources that are core resources are networks, subnets, and ports, which are those same basic abstractions that I went through earlier. Additionally, if you have extensions, we can talk about how those are exposed in a moment. The REST service is also responsible for serialization and deserialization of the request. For most people, when deploying, and from a deployer's perspective, the REST service either works or it doesn't. From a developer standpoint, the REST service takes care of a lot of the request response cycle, so that way you can really focus on implementing your plugin. Optionally, you'll have the RPC service, which is used by many of our deployments. The RPC service enables the L2 agents to talk to the main upstream Neutron server. The L2 agents in Neutron are optional. Some of the solutions do not use L2 agents, but when they do, communications via AMQP, like I said, enables bidirectional communication, and it's optional. At the box at the bottom is the plugin. If you really think about a plugin in Neutron, you can only have one. It's like having an engine to a car. It's written in Python. There's multiple implementations, but they all have to implement the same set of core V2 API calls, which are the create, read, update, and delete operations on the logical resources. Most of the plugins include database access, and almost all of them support extensions as well for differentiation. So when we go into writing code, for instance, the Modular Layer 2 plugin is the main open source plugin, and the box on the right, as you'll see, is just a snippet of config file, where basically we've set the core plugin. But really the Modular Layer 2 plugin is actually a subclass of two other classes, the parent class being the Neutron plugin-based V2. And that implementation is on the right-hand side of the screen. If you're familiar with Python, you'll notice it's an abstract class, has no implementation whatsoever other than the interface. The middle class, the DB plugin, is a common class the Neutron team wrote to provide a common database caching layer for the plugin implementations. We did this to make it easier for vendors to implement their solution. Plugins, so we have those basic resources of networks, subnets, and ports. And one of the things is that vendors need to be able to differentiate themselves. So one of the ways for differentiation is via plugin extensions, and they add logical resources to the API. The extension of a logical resource, if you're familiar with OpenStack, would be security groups, which provide a distributed firewall and protect the VIFs of each instance. The extensions can be discovered at startup, and so when you're using different clouds as a user, you can discover which extensions are enabled by hitting v2.0/extensions, and it will give you the list. Some of the common extensions you'll see are binding extensions, which is mainly an internal extension that provides the mechanism to tell Nova how to connect to the network segment for a particular instance. Also, DHCP L3 provider enables you to bridge your deployment into your existing physical network within your data center, quota security groups. Other optional extensions you'll see are allowed addresses, which prevent address spoofing, extra routes, and metering. When it comes to plugins, there's really two different flavors. We have the monolithic plugin, which implements all the core resources. It kind of has two subtypes of proxy, which takes the REST calls and proxies them directly onto the northbound API of another SDN controller, say Open Daylight, Open Contrail, or REU if you're using open source controllers. The other subtype is direct control. Direct control would be more representative of what we ship inside of the Neutron tree, which is it directly manipulates the OpenVSwitch bridge, the OpenVSwitches within the deployment. To make implementations easier, one of the things that our team's been working on over the past year is creating the Modular Layer 2 plugin. What this does is it enables the vendors just to write specific L2 drivers for the equipment for the switch, and really removes the need to write higher level stack or understand more of the request processing. You can write just the bare minimum in terms of orchestrating just the network segments. So there's two types of drivers. There's the type driver, which is basically either you have a flat network, a VLAN network, a GRE or VXLAN, and so specifies the segment type. And you have a mechanism driver, which actually handles the mechanics of connecting to that type of segment. So that kind of covers in the server. If we return back to our basic deployment, let's dive in a little bit into the L2 agent. And really the L2 agent is where I got my title for bridges and tunnels, actually manages a collection of bridges and actually orchestrates and sets up the tunnels between the hypervisors. If you're familiar with this area, this is actually the chain bridge which links Buddha and Pest, and the bridge literally goes straight into a tunnel under Buddha Castle. So with the L2 agent, it's going to run on a hypervisor. It's responsible, it's going to watch and notify the Neutron server when Nova adds and removes devices from the hypervisor. And when those devices are added or removed, it will then wire them to the appropriate bridge. ensuring that it's on the proper network segment. So again, we get tenant isolation. In the case where security group extensions enabled, it's going to apply the security group policies. For isolation, there's several different options that deployers have. You can use VLAN, which is 802.11.802.1q. I say limited here because the spec only allows you 496 VLANs, but in reality you get much less because we reserve some VLANs for special use cases. Also, as well as your switches within your data center have to be specially configured if you want to use a wider range. For some situations, this is perfect because for certain deployments, you may not have a high degree of tenants. If you're, say, deploying a public cloud or have many different applications which require isolation, this could be a huge problem. Additionally, if you're using VLANs, your underlay has to be aware that you're using VLANs. Your ports within your switches have to be configured. Your managed switches have to be configured as well. And so some optionally choose to use GRE or VXLAN and use tunneling. So if you're not familiar with tunneling, what you're taking is you're taking a layer 2 packet, encapsulating it layer 3, and route it in that case, it looks as if any other IP packet within the data center. One of the advantages is it's routable. So when it gets into data center design, you can actually have an L2 domain per rack if you want to limit your L2 domain size. As well as if you're expanding deployments, since the packet's routable, you don't have to configure switches sorry, can't talk today. You don't have to configure the switches to be aware of what the tenant network needs to look like. The underlay and the overlay are completely isolated and separated, and you can actually have the underlay engineering can be done independently and ahead of time. So when we take a look at tunneling, let's say we have hypervisors A, B, C, and D. If we were to create the tunnels between all the hypervisors, the L2 agents have done so. One of the things we do in Neutron with the L2 agent is what's called L2 population, where we pre-populate the ARP table. But before the population, let's say you have two hypervisors, or you have two instances, one running on hypervisor A and one running on hypervisor D. If a packet needs to go from A to D, the hypervisors, what will happen currently with the tunnels is we have to flood the packet across all hypervisors trying to locate that instance. With L2 population, what we're able to do is we precede the ARP cache, and so the packet is transmitted directly from A to D. Several benefits of that is it reduces the amount of traffic on your network, and you get better resource utilization. Occasionally, or several times we've mentioned OpenVSwitch today. If you're not familiar, OpenVSwitch is an open source virtual switch. The kernel module is found in almost every major distribution, and some of the newer kernels actually ship OpenVSwitch as part of the kernel versus a module. If you need more information, it's available at OpenVSwitch. It manages VLANs, GREs, and VXLAN. Alternatively, there is an implementation in ML2 that uses traditional Linux bridging utilities as well. That will provide VLAN and VXLAN support. Oops. So if we return to our diagram again, let's take a tour into the layer 3 agent. But before we dive into how layer 3 agent works, it's important to kind of look at how we've implemented isolation. And one of those things is we use Linux network namespaces frequently. So Linux network namespace is an isolated copy of the network stack. The work was derived from the same work for doing containers. It provides a private loopback as well as a limited scope. So that way, whatever processes are running within that namespace, we'll see the network stack and the network topology as it appears in that namespace. And you can reuse addresses. So in the picture here, if you have namespace A and namespace B, each 0 in both those namespaces could have the exact same IP but be independent of each other. If we need to connect those things, then we actually have to explicitly connect them. Typically in Neutron, you'll see a bridge called brint. We will use VS and patch them together. And then that provides connectivity from the host networking into the namespaces. And as I said earlier, the processes can be spawned within the namespace. This is very useful for running agents such as DNS mask or metadata services. The L3 agents run currently right now on a network node. We're working on distributing that so that you get an increased amount of north-south bandwidth. They use namespaces, and the metadata agent will run within that. So as how we implemented it, again, it's isolated IP stack. So we'll have so the L3 agent will actually manage a collection of these namespaces on a network node. You can distribute them. You can have multiple network nodes, but each tenant network only gets one router currently. And we've enabled forwarding. The one thing I want to call out here is it says IPv4. In Icehouse, we support IPv4. For IPv6 is coming in Juno. And it's static routing, not dynamic routing. So you're not going to find BGP. You're not going to find OSPF. There are teams within our community currently working on adding support for that. And like I said earlier, the metadata proxy is typically run there. So in Icehouse, which we just released, some of the new features and some of the things you'll find is we have 4 new plugins available that's for the 19. We spent a significant time during the Icehouse cycle working on stability, ensuring that the processes run stable at heavy load, as well as that they're very performant. Another initiative from the community is all of our plugins are tested externally from the vendor. So when code changes come in addition to the main OpenStack integration gate, the third-party systems will run tests as well. So that way, you as a deployer and operator know that the code you're getting has been tested and works. And kind of opening up the crystal ball and looking ahead to Juno, the scene on the right, I'm actually from Atlanta, Georgia. That's my hometown. And so Juno is north of Atlanta in the mountains, very tiny, tiny community. I had to find a map to actually find it. So one of the things we'll be seeing is Nova network migration. So if you have a current Nova network deployment right now, when Juno's released, there will be a migration path depending on your Nova network configuration that will convert your Nova network into Neutron. This is one of a fulfillment of the promise that the Neutron community has made to OpenStack in general, which is let's provide one way of doing network, one service versus having the dual services that we have now, as well as distributed virtual routers. Like I said earlier, what this does is it enables a higher north-south bandwidth for instances. So if you have a floating IP address and you add that to an instance, that instance now has the ability in certain deployment configurations to get a higher level of bandwidth. So in scientific computing or in situations where you have you have servers with a high traffic, you can provide higher throughput and higher traffic and higher bandwidth to them without having to go through a central network node, without having a central point of failure. IPv6 is another one of the features coming. The folks at Comcast have been working at deploying this. They're currently running IPv6 privately and are working on making sure it works upstream for everybody, as well as multi-vendor service support. So in our load balancing, our VPN, and our firewall services, right now it's hard to run multiple vendors, but as operators, we want the choice of deploying multiple vendors. We also want to hide which vendor choices we've run if we're a public cloud. In a private deployment, we may not care as much which vendor we use, whether it's vendor X, Y, or Z. We don't really care, but in a public cloud, they want to have the ability to change out. So we'll have multi-vendor support. Lastly, more information if you're interested. The Cloud Administration Guide for Neutron is available at docs.openstack.org, and the network API, if you're interested in how the calls are actually structured, are developer.openstack.org. So, and I know it went kind of fast with slides, so they're available. I posted them. Questions? Yes?
What are the tools you will use to debug configuration?
So the question is, what are the tools I use to debug configurations?
Configuration, what code files do you use?
Yeah, so some of the tools we use to debug, the first question I'll ask when debugging is which backend you're using, because that's going to dictate which tools you have available. Some of the vendors have really good graphical tools which help you. Some of the vendors don't. But typical tools that I'll use when debugging the open source, I'm going to use TCP dump. I'm going to use, since we use network namespaces, I'm going to use IP utilities. So IP net and NS will get you into a namespace, and you can list them on a hypervisor host or on the network node, and it'll list which namespaces are available. So I will open up a bash shell within that namespace and then open up TCP dump so I can capture data or capture traffic and then analyze it to make sure that the packet flows are working as appropriate. Additionally, In some cases, I'll look at, if it's IPv6, I'll look at the neighbor tables. If it's v4, I'll look at the ARP tables, as well as traditionally looking at logging, IP tables rules as well. I mean, it's the same set of tools we've used for a long, long time for debugging network issues. The main kind of tweak that we've done is that you have to know which namespace to enter to kind of listen to. Yes? So the question is I mentioned that only one plugin can be active at a time. The reason for that is the REST layer delegates all calls for the core resources of network subnets and ports onto a single plugin. And multiplexing those, if we're going to have multiple plugin support, is a little tricky because each of the plugins supports a different set of extensions. And so the user experience is how would a user discover which extensions enabled for which resource, and what happens if a plugin didn't support it. So the approach we took to allow more multiple vendor support with multiple technologies was using drivers within ML2 so that you can have multiple mechanisms that implement the L2 layer, and that enables more multiple vendor support. It's also a much easier path to implementation, as well as on the operator side for deployment, you can just enable more segment types or more mechanism drivers as you build out your data center and have different technologies. Any other questions? All righty, thank you.